But expressed in polar coordinates, that's just r squared. So those are the limits for x. That just comes straight from this, but translated into the polar coordinates for y and z. So x cannot be the outer variable because its limits are not constant. R and theta, we can pick either one of those to be the outermost. It doesn't matter. So we'll make this y squared z squared r dx dr d theta. X goes from 0 to 1 minus r squared, r goes from 0 to 1, theta goes from 0 to 2 pi. But then the last thing that needs to be done is to write y and z in terms of r and theta. So we actually get r squared cosine squared theta sine squared theta times r, so we're actually going to get an r cubed. So that's the setup. The questions on the setup before I do anything else? I know. Okay. So one clue is anytime you see sums of squares like this, like if it's a sum of two squares, x, y, x, z, or y, z, that's a hint for polar or cylindrical coordinates. Anytime you see sum of all three of them squared, that screams spherical coordinates. And if you don't see any of those, chances are you're just going to do it regularly. Okay. So, due to time, I'm not going to do the whole thing, but to start it off, none of this depends on x. So, you can pull things out as much as you can. Like, the thetas, theta is the last variable, so you can put those here inside the outermost integral. And then r, you have r cubed going out here. And then the innermost integral, you're just going to have 1 dx dr d theta. So your first integral, because there's nothing involving x, that's going to be particularly easy. You just take the difference of the limits. So this turns out to be 1 minus r squared. So now, you're going to integrate r cubed times this. So that's r cubed minus r to the 5th dr d theta. So this would turn out to be 1/3 minus, 1/4 minus 1/6, which is 1/12. So and then you have a nice little trigonometric exercise. So, well, you can convert that to 1/4 sine squared of 2 theta, and then rewrite that in terms of a cosine of 4 theta. So it's kind of bad, but that's probably the worst it'll get. Well, okay, I'll tell you what. I'll put those are those trig identities on the exam. The double angle stuff. I think you're likely to use. Okay. So, questions about that one? Number 50 in chapter 12 review. So, you have a region bounded by these planes, x equals 0, y equals 0, z equals 0, and the surface square root of x plus square root of y plus the square root of z is equal to 1. All right. So, all right. So something that's contained right here in the first octant. So it's going to look something like this. For instance, if you set all right. So for instance, suppose you set z equal to 0, then you have the square root of x plus square root of y is equal to 1. Now, x squared plus y squared equals 1 gives a circle. X plus y equals 1 gives a line. Square root of x plus square root of y equals 1 is going to give something kind of freaky like that. So it's like you're taking a circle and you're punching it in. And then you have, similarly for the other pairs of planes. So it's something like this. All right. And you're computing the volume. All right. Now, that's going to be a bit of a pain to set up the limits for that. So we're going to use a change of variable. So the change of variable is going to be x is u squared, y is v squared, z is w squared. So when you do that, you're warping this into a tetrahedron. So you get u plus v plus w is equal to 1. So this warped surface now becomes a plane, or like so the front face of it would just be a nice triangle. Okay. So you also have these constraints. It's bounded by u equals 0, v equals 0, w equals 0. So all of this suggests what the limits are going to be. So we have u, v, and w. So there's your tetrahedron. And if you look at it from above, then you're looking down and you see this. So that means the volume you're going to be integrating, the function you're integrating is 1 because it's volume. So the outermost limits, u will run from 0 to 1. So you see that just by the extent of the solid. Now, for each u, we have u plus v is equal to 1. So v is going to run from 0 to 1 minus u. And then for the limits in w, use this. So w is going to run from 0 to 1 minus u minus v. So those are the limits. And when you have a tetrahedron, it's always going to work out this way. You're going to have constant limits for the outermost. Then when you so then what you can do is because this is what the tetrahedron looks like when w is equal to 0. That's how you can get the limits from you get the limits for v. So you set w equal to 0 in here, and you get u plus v is equal to 1. The unfortunate thing about these problems is there really is not much of a substitute for just drawing it, which can be kind of a pain. All right. Or seeing so many examples that you get the idea that way. Because if this had been a different tetrahedron, like one that's just sitting up there somewhere in space at whatever angle, this would be a whole lot harder.